Okay. So lesson 6, right? That's what we're gonna do today, chapter 6. So we're gonna review the ultrasonic techniques, right? Materials used in manufacturing of industrial products can sometimes have characteristics that adversely affect the product's intended performance. For example, small crack in steel used to build a bridge can grow to a size that reduces the structure's strength to a fraction of what needs to be for safe operation. Okay, so with ultrasound, we're going to try to pick all these defects, right, before imminent failure, right, and just to prevent the cost and lives. Now, ultrasound, we're also going to use it a lot in the production process, right, to avoid having the production go to a point where it's too far to, okay, like we don't want to find a problem in, let's say, in a part of steel once it has been machined and it has been worked, right? If we could have picked it up before we did all these processes, right? So it saves time and it saves a lot of money also in the production process if we're making a part. Okay. So this illustration, right, shows an ultrasonic testing system which uses the 5 elements of NDT, right? In this case, we have the transducer being our source of energy, right? Our transmitter, right? In this case, we have a through transmission setup on your screen, right? And obviously, this would be your transmitter, right? And it's a setup of a through transmission because we know that both of my transducers are perfectly aligned to each other. One's being the transmitter, and one is being the receiver, right? If this was a pulse echo technique, right, we would not have this receiver here. Instead, we would have an interface of the metal, right? And this transducer would be a transmitter and a receiver, right? It would act as both. So then we also have the probing medium, which is going to be our waves. Those are the ones that are going to be traveling through our material, right, to do our inspection. And then you have the modifier being the discontinuity, right, or the reflector in your material, right. And lastly, right, we have the sensitivity detector, which in this case, because it's a through transmission, right, we say it's the receiver on the other side of our test material, right. So obviously our test material would be composed of something similar to this. Right. This is what we're checking. And this is our defect here. Right? And we know that no discontinuities behind this discontinuity are going to be sensed by this setup, right? Unless of course this discontinuity is underneath or extending farther out than this the top one did, right? And this is going to be our initial pulse, right? And this would be our signal that it's being received, right? Now, if we didn't have this discontinuity, maybe this would be a higher amplitude, right? But because we're losing sound here, that all this sound is reflecting back, right? We're losing all this sound, so we're just getting the sides. Now our indication is going to come all the way. It's going to lose amplitude as it did in this example. Now, if this discontinuity were to go further out, right, because all the sound would reflect back, we would have no sound hitting our receiver, and in that case, what we'll have is the initial pulse, and we would have no back wall indication. Well, this doesn't have the back wall, but no energy would be received by our transducer, right? So the first element is the source of energy that creates our ultrasound, right? And we know that in our case is going to be the piezoelectric material in that transducer. We said that that piezoelectric material, right, when we apply a pressure to it, is going to vibrate, creating those ultrasonic waves, right? And we know that the diameter of that piezoelectric material and the thickness, right, is what's going to give us the characteristics of that transducer as far as what beam spread is going to be and frequency, right? The thinner your crystal, so the thickness of your crystal, if it goes down, right, your frequency goes up, okay? And again, also, if we know that our thickness goes down, right? I'm sorry, if it goes up, then we know that our frequency goes down, right? And we had also mentioned that transducers that have very high frequency, right, are very thin, and whenever they get so thin, we use those transducers a lot of times to do immersion testing, right?
One.
Yeah.
I hate to cut you off, but everywhere that you're writing right there, all that you're writing is being covered by the icons that they have, with the speaker and the camera and all that. So I don't know if you could write that like between ultrasonic testing and the paragraph that says the first element.
Okay.
I mean, it's okay right now, but just in the future, just so you know that top portion up there is always covered by those by the icons or
Gotcha.
whatever you want to call them.
All right. Yep. Thank you.
Okay.
Okay. So again, my thickness, if it's very thick, my frequency is very low. If I have a very high frequency, I should have a not very thick lens, right? And again, when we go to very thin materials, to very thin, to very high frequency to very high frequency, correct, right? And the thickness are of our crystals are very thin, is not very great. We want to protect that crystal, and instead of doing a contact testing in which you're running your transducer, you're sliding your transducer back and forth, right, to protect this crystal. What you do is you put it in an immersion system, right, in which you have water, and then you just put that transducer in water, right. Now there's other reasons why we use immersion testing other than that, but that's also one of them, right? When we go to very high frequency transducers and our crystals are thin. Okay. And we know that with our machine we could control the pulse length, right? How long that pulse, if it's a pulse echo technique, we can control through the pulsar how long this each burst of energy coming to that transducer, right? And thus we were controlling the length of that pulse coming out, right? We can also on our machines we set our frequencies, right? And we tell our machine what frequency transducer we're using, right? The ultrasonic wave, representing the second medium, the second element of the test method, is referred to as the probing medium, right? So then those would be our waves going through our material, right? They are the ones that are going to penetrate our test object, right, in search of clues of the presence of discontinuities or different conditions, depending on what we're looking for, right? Maybe we're not really looking for discontinuities. Maybe we're just looking for thickness. Just because you're using ultrasound doesn't mean you're always looking for a crack. right? You could be, maybe they did a blend out. Uh, there was a little corrosion here, so they did a little blend out, they sanded a little bit, right? So then you put your ultrasonic probe here to see what that thickness is versus the thickness, the original thickness, right? Original being from wall to wall, and this one being from wall to the new wall, right? Created by that blend out that we did. So our probing medium is going to be our ultrasonic waves. Right? The third element of ultrasonic testing is the modifier, or some material feature, such as discontinuity that alters the ultrasonic waves as they pass through a test object. So our modifier, right, is going to be our reflector. In this case, sending our this energy back to the transducer, being if it was a pulse echo technique, right? Well, in this case, right, the modifier also, it's the one that, in the pulse echo, this being the transmitter and the receiver, it would pick up the sound wave and it'll give you another spike up here. Being a through transmission, what it does is, if you have any type of break in that path of sound, right, is going to affect the amplitude of your of your of your of your spike on your screen, right? Because you're losing sound. So it's gonna either, if you have a loss in sound, your indication amplitude it tends to go down, right? And then you have, the procedure will tell you, right, if from here you calibrated this at no discontinuity to be at 100%, let's say, right? They tell you that if your amplitude goes anything below 40%, let's say, to discard the part or consider that a problem, right? So you do your inspection. If this is what you see and it's below your 40 threshold, you'll just go ahead and reject that part based on their inspection criteria. Right? Now, if this indication gave you 50%, right? This is your 40 line, and this would be your 50%. And your inspection criteria told you that anything below 40 is bad, and you get 50, well, in that case, your part is not rejectable. You'll make a note of it, but that part can still be in use, right? And the fourth element, is going to be a sensitivity detector, capable of registering changes experienced by the probing medium, right? Forgot to mention something. I'm sorry. I forgot to mention something about the modifier. Let me see. Okay. Yeah. In the case of a pulse echo technique, right, we know that the impedance ratio, right, is going to be the impedance ratio between our defect and the materials around it, being this material and the air inside the crack, if it's a crack, that would give us the reflection ratio or percent that would reflect back into our transducer, right? Our impedance ratio would always tell us how much transmission you have and how much reflection you're going to have off that interface. So we're going to have an interface in a pulse echo technique. So forget about this. We're going to have a difference in material impedance, right? And impedance, right, is the density times the velocity. That's how we find the impedance of a material, right? And so in air, we know that air, because it's filled with a crack, if it's filled with air and metal, the velocities and the impedance ratios, right? We had a formula that said the reflection reflection equals impedance 2 minus impedance 1 over C2 plus V1. And if I'm not mistaken, these two were also squared. And that was going to give us our impedance ratio back into our reflection ratio that was going to reflect back. We know that anytime we have an air and metal, right, our impedance reflection ratio is going to be nearly 100%, right? And that's why we don't get a lot of transmission, and we get them to reflect back into our transducer. Right? That's the same reason here why in this setup, right, these waves are going to reflect back, and they're not going to go through, right? If there was an impedance ratio in between these two, the ultrasonic waves would just go right through them and get to the probe, and then you would never see a change in your amplitude over here, right? But because you have an impedance ratio, you get all that reflection going back, never making it to the transmitter, to the receiver, right? And the fourth element is the sensitivity detector, right, which is capable of registering changes experienced by the probing medium. Okay, and that would be in this setup, our transducer being the receiver, right? And of course, again, we have a through transmission here, right? Setup, and in this case, we're going to be sensitive to discontinuities such as voids, right? Separations of the metal, right? In this direction. We had said also if our defect, it's parallel to the sound wave in this setup, right? We would probably not be able to see it because all that sound is just going around it, right? You're still making it to the transducer, right? So we're going to be most sensitive when our indications, right, are perpendicular to our sound beam, okay? And obviously our fifth element would be the readout display, right, which is going to be the one that's going to get all this information from our waves, right, and it's going to show it to us in a manner that we can interpret and make decisions, right? It says that the basic ultrasonic testing instruments displays the pulses, the amplitude, and time of arrival detected by the amplitude receiver, right? The amplitude would be the height of our spikes, and the time of arrival would be on our time base. We had said that our time base was our horizontal line from this starting of the screen to the end part of the screen on our machine for our equipment, right? That's going to be our time base, and the amplitude would be on the vertical scale, right, from the top, or from the bottom to the top, right? So this would be the amplitude, right? And that is the height of our spikes. So ultrasonic instrumentation. Right? Today, there are many configuration variations to consider when choosing ultrasonic testing equipment. The miniaturization of electronic components and the ability for computers and ultrasonic systems to interface have broadened the equipment options. Probably where you're going to be using out there, right? It's going to be something somewhat similar to what you saw when you took your test, especially for Augie. Mike saw it when he came over here at some point, and we played a little bit with the ultrasonic machine. That blue instrument that we saw, right? So ultrasonic testing instruments have three basic functions, right? We want them to produce an electrical pulse that is used to generate the stress wave in the transducer, right? We know that this pulse is the one that's going to create the wave, right? But however, that's only if we have a transducer. If we don't have a transducer, or if we don't have that piezoelectric material in it, then we won't be able to generate that wave, right? So this is the It's not going to do anything, right? It's just going to be an electrical pulse. And right, so so our machine is going to produce that electrical pulse. Is going to go, right? It's going to amplify. Now, once that signal goes into our material, it comes back. It hits our back wall. It comes back into our transducer again, being a pulse echo technique, let's say, or even if it was a through transmission. Once it gets to the transmitter, okay, our signal is going to be very weak due to uh, different factors, such as maybe there's a discontinuity, right? And you're not getting, right, all this. This is your sound beam. Let's say this is your transducer. So let's say like this, right? And then you have your other this is the through transmission, right? All your energy on this is going to reflect back, and the only energy you're going to be picking up is this here, right? So the amount of energy that this transducer, this is the transmitter, the amount of energy that my transducer it's sending here is not the same energy that my receiver is receiving, right? So because we're picking up so very little energy, right? And you also have to keep in mind all the attenuation factor, right? That's by the material, right? And because of that, my weak over here is going to be very weak. So our machine also needs to amplify the weak echo signals received from within the test object, right? Or if in the case you had only right a pulse echo technique, right? You're going to come over here. You're going to go back down, right? The signal that comes up here, all this trip, and in this trip, right, our signal is going to get very weak due to attenuation. And so the received signal is going to be very weak compared to the one that was transmitted in the first place. So we want our instrument to amplify that signal, right? And that's going to be on a receiving circuit of our equipment. And lastly, right, we have the display, which which is going to return the information, which is going to get all that information, right, that we amplified, and it's going to return the information in a meaningful way, right? It's going to put it in either in an A scan, right, or maybe it's going to put it in a B scan, and this would be all color, right, or maybe a C scan, in which you have that automated, right, inspection or scan path, and then you have different shades of gray or even color, and it's going to show you different, right? If we have different discontinuities here, there'll be different colors. Let's say this would be red. Let's say this would be blue. Let's say this would be black, and maybe my good background would be green, right? So this would be my A scan, B scan, and C scan, right? And our display, right, is the one that's going to do that. It's going to transfer all this information and make it into a way that we can read. All right, so our display is going to be the one that's going to get all that information and put it in a meaningful way. So the ultrasonic testing has a pulser, an amplifier, and a display. Right? So here's a basic ultrasonic equipment, right? Or this is how it works in the inside. Mike, put your thing on mute for a second, please. Thank you, sir. So this is going to be a basic ultrasonic equipment, right? We have our pulsar, we have our amplifier, we have our display. In this case, it's showing us an A scan, right? And even if we didn't have this, we know it's an A scan by the way our indications are look, right? We say that the X line here, or X axis, would be our time base, right? So this is in time, and the y-axis would be our amplitude. Right. So something to keep in mind here is that, and then we have our clock, right? Which our clock is going to be the brain of our equipment, right? It's going to be the master, and you can see how everything's working out of the clock in the sense that no lines are going into our clock, but except he's only sending lines out, or right, nothing's coming into him. So he sends the signal to the pulsar, and when he does that, he starts counting and sending that information over to your display. Right, the pulsar comes down to your transducer. It hits that piezoelectric material, or element, or crystal, right? Either name. That's going to create that wave. Obviously, we get a half coupling, right, between our transducer and our part. Ultrasonic waves will go into our material. In this case, they'll go down here, reflect back, and the ones from this discontinuity will stop at this interface and reflect back, right? Because the air within that discontinuity, right? That indicates those signals will come, make that transducer vibrate again, and when that crystal vibrates, it creates another electrical circuit, right? Now it's going to be it's not going to have the same intensity as the first one that came out, right? Or the first one that came in. So it's going to send that into our amplifier. Our amplifier is going to amplify our signal received, right, by our transducer. Not only is going to amplify it, but it's also going to filter it, depending if we want to filter certain indications, certain frequencies, right? If we want to use reject, and then that information, once it's processed and cleaned, is going to send it to our display, right? And it's going to be showing us a thing, right? In this case, this would be my initial pulse, right? This would be my back wall, and this would be my discontinuity, right? And we know that, right? Our inspection area would be from an interface or a back wall, meaning from our interface, the front surface, to the back wall of our material. Right? So we're inspecting anything that's in between those lines. So any spike you have in here is a reflection of sound within this surface and the back wall. Okay. So pulsar. When triggered by the clock circuit, most pulsars emit a sharp, unidirectional, or spike pulse that is sent through a coax cable to a transducer. In most flooded instruments, the pulsar is adjustable to adapt the instrument to different testing conditions, right? So the pulsar, right, is gonna send that, is the one sending that pulse to our crystal, and in especially in the instruments we're going to work now, those modern instruments, and even some old instruments, you're going to be able to adjust the pulse characteristics, meaning how much pulse you want, how strong you want that pulse to be, right? And that's going to give you how much penetration you're going to have also, right? Because the more pressure you put in that transducer, the harder it's going to try to penetrate that sound wave is going to go. Right? The more pressure, your wave would tend to come out a little harder and penetrating a little more. And also you can control dampening factor of it, which is the pulse length, the length of that pulse, right? So for longer pulses, right, we're not very sensitive to the front surface, right? At least for defects, very shallow defects, right? For example, on here you can see how this one, this is your initial pulse, right? And you can see how broad this is, and that tells me that this pulse, right, has a longer pulse, right, or the dampening setting, it's greater than the one over here, right? And look, we both have, this is at the same frequency, right? We have indications at the same distance from our surface, right? And the only thing that's changing is our pulse. As far as the pulse is being short, this is here our pulse is going to stop, right? And if this is a longer pulse, and that's why even though you have an indication here, right, it's being covered by your whole pulse, right? Because your pulse is going from here to here. It's exaggerating a little bit, right? But from here to here is your pulse length, right? Which is going to be from here to here, right? And because you have that indication in between, it's being covered by that pulse, and you're not going to be able to see it, right? So if this is near the surface and you have a long pulse, your near surface resolution is going to be very poor. You're not going to be very sensitive. However, if you have a short pulse, if you're dampening, right? If you have a short pulse, then the same indication, just because you have a shorter pulse, right, you're going to be able to see it clearly because it's not being hidden by that initial pulse, if it makes any sense, right? If you have if you have it on this type of display, right, we say that display is our RF or radio frequency, right? You can see how a short pulse, right, you have a short, sweet indication versus this pulse that may be greater, right? Now, remember, with this, you may have a little more resolution, but you have a little less of penetration. With this one, you have a little bit higher penetration, but then your sensitivity, your near surface resolution for defects is going to be lower. So the amplifier. The amplifier boosts the signal strength of the received echoes to a level that can be easily displayed on the instrument screen. It is adjustable. It is the adjustable gain of the receiver section's amplifier that is a key variable under control of the technician, right? And usually it's measured in decibels. So our gain, being the volume in our radio, right, is the one that's going to increase our indications, right, in decibels. Now, I had also mentioned that when you increase volume, right, if your radio is not perfectly tuned, right, and you get some kind of transmit, how can I say it? If you don't get a clear reception on or sound coming out of your radio, right? If you increase your radio, not only you're increasing the volume of your song, let's say, or whatever you're listening to, but you're also increasing that hash sound, right, or that mic mute.
I'm sorry.
Thank you. Right.
Are you good? Is it muted?
Yeah, really good.
On.
Yeah.
Is it muted?
Yeah, you were in mute. Not anymore though. Okay, you're good now. All right. So, and we're gonna measure that gain in decibels. Right. We have a formula that says 20 log, and this is for amplitude, right? Amplitude 2 versus amplitude 1. And we're going to work with this formula later on. But this formula, right, it tells you that if you, let's say, have this at 40%, and this is your initial pulse, let's say this is your back wall echo, let's say, what gain or how much volume do you need to put to this equipment to bring this indication to, let's say, 80%, right? So we don't know how much gain. So we can with this formula we can say we can say 20 log amplitude 2 over amplitude 1, right? We had said our amplitude 1 is our starting amplitude, right? So 20 log amplitude 1, we had it at 40%, right? Our indication was at 40%, and we said we want to make it at 80%, right? So my amplitude 2, we want to make our indication go up to 80%. Or we want to increase that spike to go from 40 all the way to 80, right? So 80 divided by 2 equals, right, 2. So in that case, it would measure 20 log 2, right? And if you do this calculation, get a calculator. You get the log of 2, right? And the log of 2 would be 0.301, right? And then when you multiply by 20, right, this answer would come out to 6.02, right? And what that means is if you increase, right, your gain by 6.02 decibels, you would increase your amplitude of your indication from 40% to 80%. So you will double your indication. So anytime you increase your decibels by 6, or you add 6 decibels of gain, you're going to be doubling the amplitude of your indication, right? Now the same thing goes for, so let's try the same one. Now let's put 20 log. Let's say this time around we have it at 80 and we want to make it go at 40, right? So we're starting at amplitude 1 at 80, right? And we're trying to go to amplitude 2, which we're trying to go to 40 because we're trying to bring it down. So how much gain do I need to subtract to make my indication go from 80 to 40? So 40 divided by 80, right, is going to give us a 0.05. Now this 0.05 you're going to multiply by log, right, and it's going to give you negative 0.301, right? Now you multiply that by 20 and the indication is going to be minus 6.02 decibels. That's going to be your answer. So to go from if we have an indication at 80% and we want to make it 40%, or we want to cut it in half, we would have to subtract 6 decibels. So it makes sense, right? If we want to double it, we add 6. If we want to cut it in half, we erase or we decrease our gain by 6. Okay. So we're going to use this formula in a couple problems later on, but that's how that's our amplitude formula for gain, right? And we said that gain is measured in decibels. Okay. Although the primary purpose of the amplifier component is to increase received signal strength to meet the requirements of the sweep display unit, it is the technician who makes these modifications according to how the echoes appear on the instrument screen. Okay. So depending on how you want your indication to look or how much amplitude you want, you start increasing your gain. Now, this formula, right, the 20 log amp, right, formula, right, you don't have, if they tell you bring, let's say you have initial pulse and then you have this at 35%. Right? If they tell you bring it up to 80 or 100%, well, you don't have to start plugging all these numbers here to come up with, okay, I gotta add maybe, well, let's do this problem. 20 log, right? Amplitude 1, we're starting at 35%, and we're trying to go to 100%. So 20, 100 divided by 35, that's gonna be 20 log 2.857, right? And then once you get this, multiply by log or get log, right? And it's going to give you 20. There's a parentheses 0.456. Let's put it right. If we round it. And then when you multiply that by 20, you're going to see that you're going to need 9.12. Right? So to increase my indication from 35% to 100, I would need 9.12 decibels. Right? That's what I would need. But you don't have to be doing all this calculation, right? When you're doing it with the machine does it for you automatically. So what you can do is you press on the gain setup on your machine, and you start increasing your gain until you see this start coming up to whatever value you want to do it. But you will find out that when you hit 100%, right? If you were to record the gain you had here, right, and you start increasing your gain until you get to 100%, you can get this gain, subtract this one, and you'll see that you increase 9.12 decibels. Or if you do this formula, you could just go ahead and crank it up to 9.12 decibels, and it's the same thing. You're going to see that now this indication is going to be try to bring this indication up to 100%. Right? So once the echo signals have been amplified, they are ready to be used in a display mode that gives information about the location and nature of the echo surface within the test object. Three general formats are the A scan, the B scan, C scan, right, are commonly used, with several others incorporated for a specific type of equipment. Right? And we say that the one that we're mostly going to see out there and we're going to be working with most of the time is going to be our A scan, right? That's going to be the most common type of display. Right? So this is going to be our A scan. Right? It says that the most common display, it's the A scan. In an A scan, the vertical axis represents the signal strength, right, or the amplitude, right, the amplitude of your signals. And the horizontal axis represents the time and displays pulse signal amplitude variations with increasing time from a specific reference point. Right? So you have all your settings here, right? So this is what we were talking about, the amplitude, right? These are all repetitions of each other. Okay. In this case, for example, if you wanted to have this indication, this signal come up here to 100%, well, you can use that formula to figure out how much gain you have to add to this equipment to bring that signal up, right? So the reference point at the left side of the display, it's usually the moment when the transducer is first excited, right, with an electric pulse, sometimes called the initial pulse or main bang, and that's this here. Right? And then this is going to be our echo, our pulse length, right? Our pulse, and this over here, right? We say that this is going to be the time, the echo, right? This is the time at which that echo or that pulse, the echo of that pulse is going to arrive, right, at the transducer. Okay. So this is when it went, you have the material. So this over here is going to be this interface again when it comes and it meets again with the transducer. Right? And obviously this is your inspection, your area of inspection is going to be from here to here. Even though your main bank starts over here, right, this would be considered a dead zone because any indication that you have in between here, right, even though you're still in the material, right, is going to be covered by the main band. Right? So you're not going to see any indications in this area unless they go way out of the main band, but they're probably going to be so close that you won't even see them. Okay. And so your signal amplitude would be from here to here, right? Your inspection on your screen would be from here to here, right? And this is your mean bang or initial pulse. When the signal is displayed, it is correctly called the video signal. The bottom horizontal line is often referred to as the horizontal time baseline, right? Or the time base. This is the horizontal baseline or the time base. And we usually have it in 10 different divisions, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Either you have them in a decimal format or you'll just have them in a regular numerical standard format rather than in decimals. Right, the B-scan displays a cross-section of the specimen in relation to the probe position on the test surface. Right? The result represents a cross-sectional slice of the reflectors associated with the test object. So you're only going to see, right? You're going to on the B-scan, you're gonna see the areas that only came back to the probe. So this areas here under discontinuities, right? You're not going to be able to see, right? And you're not going to be able to see if you have any defects there unless they came out of the range or the size of your initial reflector, right? In this case, let's say we had right, so let's say we had another defect here that extended somewhat like this, right? Well, in that case, your indication will look more something within the lines of something like this, right? Why? Because you're not going to be able to see anything that's beyond that line. Right? So all this is going to be, you're not going to be able, right? Now, you're going to be able to see it this way. So this is your B-scan, right? It's a cross-sectional view of your right? And if you didn't have any defects here, there would just, this would be all black, and obviously this would be all black also. So a series of B-scans taken with the vertical orientations can be used to build up a three-dimensional image. In practical application, A particular region within the test object is usually of interest. Often a single slice is sufficient to gather the information for determining a reflector's location, general size, and shape. And with a C-scan, right, the transducer scan over in a regular pattern over an area of interest, often using automated mechanical positioning devices. The objective of most C-scans inspections is to produce a 100% scan of the defined cross-sectional or section of the test specimen. Right? And then you have an X direction and a Y direction, and you're going to be scanning, right, until you get 100% coverage. Right? And your C-scan display is going to look something similar to this, in either color or in different scales of gray. Right? And this would be your indications, if you had any. Right? And that would be depending on the color or the shade of gray. That would mean what type of depth they had, or how much penetration you had on that wave. Computerized systems. The devices used to display the various scan modes can be based on analog or digital technologies. Older instruments are purely analog and have traditionally been equipped with a cathode ray tube to display A scans. Cathode ray tube looks something like this. Okay. This is a cathode ray tube, right? You have the tube in here shooting the electron beam, right? And this is inside the machine, right? That electron tube, and it's going to look something similar to this. This is going to be cathode ray tube, right? And it's a glass screen, pretty much like old TV. It's rounded, and it's going to look something similar to this. Digital devices transform the analog signal into its digital equivalent using an analog to digital converter circuit. This process causes an inherent delay in the refreshing screen displays about 60, and this process causes the inherent delay in refreshing screen displays, resulting in a slow response time from digital systems. Okay. The digital systems can be equipped with auxiliary features that can enhance their functionality well beyond that analog systems, right? So automatic calibration, data storage, external communication. Right? This is kind of cool. You don't got to do calibrations every time you go out. So you have an inspection for a part, right? You can inspect it and you can save it on your storage portion or setting in your machine. And now all you got to do is next time you come to that inspection, you go once you save that inspection. Let's say you saved it with the name of the inspection, right? So now you know which calibration that's going to be good for, or what inspection that's going to be good for. So now you get another plane or another part of the same inspection that it requires, and all you're going to do is you go into that setting, and you press recall, and when you press recall, it's going to bring all that back up into your right, and into your equipment. Your machine is going to be calibrated again as you did last time, and you're not going to have to do it. Right? So you can store multiple calibrations, right, and it's a lot faster doing it this way than having to calibrate every time for the same inspection. Right? And external communication. Transducers. All parts of an ultrasonic test system are important. None, however, are more important than the improvements in manufacture of transducers. Right? Again, here we have contact transducers. These are all contact transducers, right? We have our wedges. Right? This would be different wedges here, and this one we can see is a 60 degree. Right? So they have different type transducers. A transducer's frequency is determined by the thickness of that crystal. The thinner the crystal, the higher the frequency. Right? So frequency is higher as the thickness of the crystal is lower. Right? And vice versa. Very low frequency transducers have very thick right? The higher frequency sound beams produce higher levels of sensitivity and resolution, but that's the ability to penetrate test objects to greater depth, right? And we say that frequency and penetration, right, are also inverse to each other. So as frequency goes up, your penetration goes down. But as frequency goes down, right, my penetration is going to go up. Right. Penetration versus sensitivity and resolution. For good penetration, use a transducer in the lower frequency range, right, less than 5 megahertz. So again, penetration and frequency, as one goes down, the other one goes down. It goes the opposite direction. So for good penetration, you want good penetration, so your frequency has to go down. So you usually want to go less than 5 megahertz. The procedure you're going to use, or the manual you're going to use to calibrate, is the one that's going to tell you what frequency to use. Okay, that's going to be a given. Unless you're level 3 and you're going to start creating procedures, you're not going to have to be worried about finding what probe you're going to use, which one gives you better sensitivity or penetration or resolution. That's none of your concerns. As a level 1 and level 2, right, you'll be working out of specs, and they will tell you what to use. Right. For higher sensitivity and better resolution, use a transducer with a higher frequency. Right? But then again, if we use a higher frequency, my penetration is going to be low, but we have higher sensitivity and resolution. Right? Damping. Transducer damping contributes greatly to its characteristic ability of either improved penetration or improved near surface resolution. Right? So again, right, so that's the length of our pulse. Right? There's a pulse echo technique. Right? The longer the pulse length, right, the little more penetration you get, but the less resolution you have. Right? The longer this is going to be, and any indications we have within that pulse length, you're not going to be able to see. And we say that from here to here, we call that dead zone, right? And we call it dead zone because that's any indication in here is going to be covered by that initial pulse, right? Versus a high degree of dampening, right, will shorten that pulse length, letting us get a little less penetration, but you get more resolution on your near surface defects or discontinuities. So in applications where good resolution is of primary importance, it's common to select a highly dampened transducer. Right? A higher degree of dampening will help to shorten interface ring down, right? Meaning this ring down here, or recovery time, and allow the system to resolve closely positioned reflectors. Closely positioned reflectors to the surface, right? That's near surface resolution, right? The summaries that follow provide a general impression of the performance characteristics of each transducer type. The technician should remember that each application is unique and requires careful evaluation. Right? So high penetration, right? It has low resolution, right? Low resolution transducers. Because you're penetrating more, your pulse length is probably going to be longer, you have less resolution. Low resolution transducers are intended to provide excellent sensitivity in situations where resolution is not of primary importance. Typically, these transducers will have longer waveform duration and a relatively narrow bandwidth. Right? We said it has a longer waveform duration or pulse length. Medium penetration, right? It's high resolution transducers. High resolution transducers are manufactured to reduce the excitation pulse and interface echo recovery time while maintaining good sensitivity at the transducer center frequency. Okay. Broadband transducers. Right? These are untuned transducers that provide heavily dampened broadband performance. They are the best choice in many applications where improved resolution is desired in the far field. Right? they want better resolution in the far field. If you're not really concerned about the resolution in the near surface, you're more concerned in the far field. Okay, Mike's still there? Yeah. Yeah, Mike's there. Okay. Aggie, you still there? Aggie? Aggie fell
I'm
asleep?
back. His fat ass better get up, man.
Augie, we're listening, man. Alright, we're good. Okay. And broad-banded transducers, right? They're not suitable in tests of coarse-grained, highly attenuated materials, right? So castings, you probably won't want to use broad-banded transducers in casting materials. So effects of transducer dampening, right? So here we have a highly dampened and a less dampened, right? Or longer pulse length, shorter pulse length. So the pulse length, right, is going to be very short and highly dampened, right? Because it's very short, you're dampening a lot. And in less dampened, you're going to have a longer pulse length, right? The frequency, 1 to 2 ring cycles, right? The range, your bandwidth, how it's going to look, right? And the purpose, why would you want to use a highly dampened transducer, right? For better, maybe resolution, right? If you're shorter, your pulse length, right? You're dampening more, you have better sensitivity and resolution for near surface discontinuities. If you have a longer pulse length, maybe you're better for penetration. You got a little better penetration, right? Test and documentation. Transducer markers makers acknowledge that transducers, even those made by the same company to the same specifications, can be highly individual. It is very important to carefully test and document individual transducer characteristics. Okay. So not all transducers are the same, right? And just because that's something that you have to keep in mind, if you store a calibration with so you have two transducers, right? And they're both 5 megahertz. So you went ahead and you performed your calibration, you stored it, right? You did your inspection. Now you saved it. Now next week you get the same inspection. And so let's say the first time around you calibrated with this transducer, right? So next week around you get the same inspection, and you just come out and you say, okay, well I have it saved, so I don't need to calibrate again. So you get all your equipment, but now instead of getting the same transducer, you get this transducer. Right? You get this transducer because it's a 5 megahertz. It's still right. It's the same transducer, at least frequency-wise and diameter-wise. But you get this one. Now you go ahead and you do your calibration. Well, your calibration is going to be very, very close to the first calibration you did, but because you're using different transducers, right? Not all transducers are the same. They're always going to be, one is going to be different from the other, even if it's the same person doing it, the same machine, the same material, the same diameter, the same frequency, the same crystal thickness, all that. They're still going to be different to each other. So if you use a different transducer, you may have to tweak it a little bit, right, to make it look exactly as you had this calibration before. We're going to be very close. I mean, you may have to add a little bit of gain or just a little less gain, you know, maybe your range, fix it a little bit. But we want to always know that our transducers are always going to be different one from each other. Today's manufacturers typically provide documentation of the transducer's actual radio frequency waveform, and frequency spectrum. Okay. So when you get your transducer, right, you're gonna, in fact, I'm gonna show you what they're talking about. Give me a minute. Okay, this is what they're talking about, right? When you get your transducer from your manufacturers, you're going to see that you're going to have, right, they're going to give you the spectrum, right, at which that transducer works, right, and they're going to give you the frequencies at which is more sensitive, right. In this case, you can see that at about 10 megahertz, this transducer, has a greater response, right, than it does at 20%, or than it does like between 0 and 10, right. And then you also have your signal waveform, right. Right. So this is what they're talking about. When you get your transducer, you get on your documentation of your transducer, and each transducer they give you this information for each transducer. So going back to the PowerPoints, right? Today's manufacturers typically provide documentation of the transducer's actual radio frequency waveform and frequency spectrum. Right, we just saw that. So when you buy a transducer, they're going to give you that. And each transducer will have its own separate or different form. Piezoelectric materials, right? The details regarding the physical and acoustic properties of the piezoelectric material used to make the actual crystal within the transducer is often held by the manufacturer as proprietary. The users of the transducers define whether the manufacturers have been successful by exercising their choice of one band over another. Now it's your choice to pick what manufacturer you want to use, unless the procedure tells you to use one in particular. Right? You can pick your own manufacturers. Materials such as quartz, lithium sulfate, and barium titanate, which were used in the early days to make transducers, are almost never used today. Instead, new powerful piezoelectric materials are used. Their basic acoustic and electric characteristics are very different. Depending on the application, one material may be more advantageous because of physical or economic reasons, or simply because of a less complicated manufacturing process. And so in ultrasonic testing is used throughout the original manufacturing process, and again, as a tool for assessing the integrity of components during their lifetime. Right? So not only do we check parts that are in service to make sure that they are good and they can continue being in service, but also we want to check them in the manufacturing process to make sure that we're not wasting time, and spending money putting some part that maybe has some internal defects to it through some processes that may not be needed otherwise. Right? In this picture, right, this would be your A scan. Right? This is your transducer. This is your part, your cable, and this little bottles here would be your coupling. Okay, your coupling is there. It's a gel type liquid. Okay. During the useful lifetime components, during their useful time life, component systems and systems are monitored for progressive degradation caused by inadvertent overloading, cyclic fatigue, cracking, corrosion, or environmental conditions. Ultrasonic testing is used throughout the maintenance programs of power stations, okay, aircraft, petrochemical plants, transportation facilities, okay, and others. Unlike light, which can travel through a vacuum, ultrasonic waves require an intermediate medium to transfer the transducer's mechanical motion to the test object. Okay, so we cannot do ultrasound in total vacuum. Right? We need molecules in our material, right, in order to do some ultrasound. So we can't do it in space, let's say. So acoustic coupling. In contact testing, right, we know this is contact testing because even though here our transducer is touching the part, and here, even though our transducer has a wedge, it's still touching our part, right? In contact testing, the transducer is in direct physical contact with the test object. Successful acoustic wave transfer is best performed when a thin layer of coupling is applied between the transducer and the test object, right? And you could see how you have coupling, right? If you have no coupling, right, you'll just have maybe all of the reflection, right, back into your shoe again, or back into your transducer. Right? You would have no transmission. You want to put that coupling to increase the transmission factor. Right? Many angle beam transducer wedge combinations permit transducers to be attached to a wedge with small screws or spring-like snap rings. Right? The wedge can be changed, allowing for various wedge angle combinations. Right? And the reason why we want to use a lot of those wedges, right, is because they're cheaper. It's cheaper to buy a wedge which is made out of plastic or a plexiglass, right, than buying a whole transducer, right? Than the little box that you guys saw, the black one, that has the transducer embedded in it, right? And then for every angle you will need it. It's a different transducer, right? So instead of paying maybe $400 or $500 for each transducer, right? It's better to pay one transducer and then just change the wedges, which are a lot cheaper. Angle beam transducer wedge combinations require high viscosity coupling to be applied between the face of the transducer and the wedge. The coupling should be the type that does not rapidly evaporate or dry out. Right? So what that means is that not only do you need coupling between your part and your transducer, but you also, if you have a screw-on wedge, if you have a wedge, you also want to put coupling between your transducer and your wedge. Right? Because if you have coupling here, but you have nothing here, then you'll just reflect it back into you have reflection back into your transducer. Right? You won't have any transmission into your, right? But you want to transmit into your wedge, and then from your wedge into your material. You want to have two couplings, right? Always there, in between your transducer and wedge if you're using one, and also between your wedge and your material. So alternative couplings, right? And this would be dry coupling, right? And this would be for air-coupled transducers, right? So spurred by the need to perform tests without the use of any liquid and coming in contact with test objects, dry coupling has been achieved with special synthetic rubber cover materials placed between the transducer and the test object. Okay, so this is another type of coupling, right? We call it dry coupling. Air-coupled transducers can be configured to work in a through transmission mode like water-coupled transducers. However, a distinct feature, right, of air-coupled transducers is usually in the 200 to 400 kilohertz range. It is able to efficiently generate guided plate waves which are otherwise rapidly dampened by water coupling. Okay. You see how low the frequency you need compared to coupled transducers, contact transducers, right? And when we use coupling that, we use 5 megahertz. This is 200,000 cycles per second. Right? This would be 5 million. So there's obviously, air coupled transducers are obviously a very low frequency, right? Because you don't have that coupling. Right? So several combinations are used to generate guided plate waves within the test materials, such as plates or tubing. And these are examples of air coupling transducers, right? Where you have no coupling, and you're just going through air to make your plate waves into your test pipe. Typical tests for air coupled transducers include, right? So we use these transducers in honeycombs, solar panels, foam sandwich panels, core-coated honeycombs, aircraft brake discs, timber, and wood products. Air coupling. Picture is carbon phenolic laminate 19 centimeters by 19 centimeters, right? The black areas indicate the laminations, okay? And we know that because of the display, we can see that this is a C-scan, right? And we know that this black areas would be delamination, right here. And it says that, and this image was produced with an air-coupled transducer, right, at 400 kilohertz, the frequency of our transducer, and it was indexed at 0.40 thousandths of a centimeter, meaning that it went, what I mean by index is transducer, it went up and then it moved 0.040 thousand centimeters to the side, and then it came down, and then it moved another 0.040 centimeters to the side, and then it went up, right? And that's what index means. And the scan speed was no more than 10 centimeters a second. So immersion coupling. With immersion coupling, the transducer is somewhat removed from the test object surface, so it's not a contact testing, right? Ensuring continuity of the sound entering the test object by the use of an intervening water path. Right? So this would be our tank, right, which would be filled with water, right? And this is our bridge, right, the one that's indexing moving, right, and indexing our transducer. Our part would be located inside this tank, right? My transducer would be inside the water, right? There's got to be a watertight, waterproof transducer, right? And it's going to use that water in between the part and the transducer as the coupling for that sound to go through, right? Immersion systems are widely used in the metal manufacturing industries for offline tests of billets, bars, and plates. They are also used for fabricated parts such as jet engine turbine blades, right? So again, this is a massive setup, right? This is your bridge, and this is maybe a plate. They have sheet metal, right? And you're just moving that transducer left and right as this is moving forward. So this will index, will make one travel, index, travel, index, travel, index, travel. And maybe this will put out a C-scan, right, to tell you what kind of defects you may have, right? Let's say. Now, that's immersion coupling, right? We're using water as our coupling. And another form is the squirter system, right? In which we have a water column, right? And we have two transducers, so we have our part. Right? And then we have a little water hose connected to this, and water will be filling this cavity up, right, and overflowing, right, on both sides, and one would be the transmitter, the other one would be the receiver, right, and it'll transmit through this water path into our material, and then go back into the water path into the other material. And this is also considered an immersion testing, or at least an immersion technique. Right? And we know this as the squirter. It is most often used with the transducers aiming pulsed or continuous sound beams through water columns that carry the beams to and from the surface of the test object. Base material testing. On large plates, it is common to perform straight beam tests, right, using a grid pattern of scanning. The grid is laid out in accordance with governing codes or specifications, and the transducer is moved along those grid lines. So again, this is a contact, right, straight beam. We'll scan, index, scan, index. It is also necessary that adjacent base material in welded assemblies be tested for laminations prior to performing shear wave test of the welds. These codes mandate the scanning for laminar flaws prior to the performance of weld inspections by the use of shear wave. ASME and AWS codes will be explored in the next lessons. Okay, so here, let me see. So when performing angle beam test on plates, a full test will require scans in 4 directions, right? And this 4, one coming this way, the other one going the opposite way, and then checking for flaws in this direction, right? And checking for flaws in this direction, right? To detect, so we're going to scan in those 4 directions to detect discontinuities aligned both parallel and they're perpendicular to the rolling direction, right? Rolling direction being process in the manufacturing process of the material. So this is a plate, right? And what a plate is you have 2 rolls, right? And you have, kind of looks ugly there. So you have this material, right? And these rolls are rolling, obviously. And as they're squishing this material into this specific thickness, right? And this is called rolling, right? And then this would be your final product, right? So let's say this material, it was rolled from here, from this material down to this thickness, right? So now you want to check for cracks, right? You want to scan in 4 different directions if we're doing angle beam, right? So angle beam testing of a pipe is performed in a similar manner, with 2 scans around the circumference in opposite directions, right? So you want to scan going this way and going this way along the circumference, right? And in 2 opposite directions parallel to the axis of the pipe. So you also want to go along the pipe, right, axis, meaning to the back and forth. On the circumferential scan, a wedge specifically contoured to match the pipe's outer diameter is usually required, right? So on here, because you have this curvature, right, the wedge of your transducer is going to be rounded, right, to the same radius this pipe has, or the same curvature this pipe is, right? Otherwise, you would not have full contact. In this case, you wouldn't need that because you're going along the axis of the material. You don't have that curvature, right? So beam weld, a straight beam testing. Straight beam testing of welds can only be performed on welds that have had the weld reinforced ground flush or are from the backside of a T or corner welds, and then only permitted by the governing code or specification. So what they mean is, if you're gonna do straight beam through the weld, meaning you want to put a transducer here, and you want to shoot to inspect the way the weld, right? On this type of weld, right, you want your this here to be flush, to be ground flush, so you can set your transducer flat on that surface, right? Otherwise, you wouldn't be able to set it flat on it, right? And if in the case you're doing a T or a corner, this would be a corner type setup, right? You want to inspect from this face, so you should sound through here and through your weld. Right? And if it's a T fitting, if it's a T setup, you also do it from this face, right? So again, check from here to here. So on here, only if your ground is flush. If this is flush and straight, you can put your transducer on top and just check through your weld. If you have a corner or a T fitting, you want to do it from the other side, right, from the opposite side. Angle beam testing can be performed on full penetration plate butt welds. The first step in the testing process is to determine the accessibility and area of interest, right? So we want to know how much access we have and what area we're concentrated on, right? So you want to see if you have access to this, right? And you want to know what you're checking. Okay. You don't want to be inspecting from here in a longitudinal wave, right? If your wave is if your weld is over here, right? Instead, what you would do in this case is you would, if you want to shoot from here, you'll shoot at an angle, right? So you have two different configurations of weld, right? You have the V butt weld, which is this type, and the double V, right? And obviously, it's obvious why they're called V butt weld, right? It looks like a V. And we can inspect them from this four surfaces, right? And you would put your transducer here, right? And what you would do is you would shoot at an angle into your wave, and as you move this transducer back and forth, right, you'll be shooting at different. You'll be inspecting different sections of your weld, right, depending as you start moving back and forth, right? And the same thing here, right? And obviously it's the same thing with this double B butt weld, right? You'll put, what they mean by this faces is the faces at which you would inspect, okay? So picture here is a typical corner weld with a scanning surface A, right? Being on the weld crown, this is the weld crown, on the bubble plate, right? The B face being the opposite side of the same plate, and face C being directly opposite to the bevel plate on the reverse side of the adjoining plate. This would be, so if they tell you to check from face A, you would obviously shoot at an angle. If you're shooting from plate B, you're obviously shooting at an angle. And if you're shooting from face C, you want to be shooting straight beam. Right? You don't want to be shooting at an angle. You want to shoot straight beam. The phase designations are the same for a T weld. Right? Again, this would be straight, and this too would be angle. Angle beam. So you might use a couple wedges here, right? And you need to know what angles you're going to be shooting at, and depending on your angle, you may need, because you need to scan your probe back and forth to get all these different, right? Let's see. To get full coverage, let's say you need to scan from here to here, right? So you need all this access in order to shoot or to scan this whole weld from face A. You need all this access on this face of the material. So if you have anything on the way, you're not going to be able to scan all this surface or all this area, right, using this face. So it's important to know what angle you're shooting at to determine how much of an area you need to scan to make sure you get complete coverage of your weld. Okay? Once the scanning space has been selected, it is necessary to determine how much of that surface will be needed to scan in order to perform a test that provides full coverage. Right? That's what we said. So in an example A2, right? In here in scanning A2, and in our position A1, right? We'll be scanning about this area, and A2 you'll be scanning up here, right? So as you start moving this forward, right, you're still scanning. Right, so you need all this area in order to scan the whole thing, and that is the minimum scanning distance you need, right, to make sure that your whole uh, inspection area is covered, right, of your weld. As the transducer is moved away from the weld towards position A2 and B2, respectively, the sound beam will cross the entire cross-section of the weld, resulting in full coverage of the weld body. Right? That's what we said. The portion of the plate to be scanned must be free of any loose scale, rust, or other foreign material that might cause a bad coupling, thus preventing sound from entering the test object. If weld spatter is present, it may be necessary to remove it prior to the test. What weld spatter is just when you weld, you may get some splash of that material, okay, and you'll see it on your surface, right? It looks like little droplets of metal, right, of whatever metal you're using to weld, and you have to clean that off in order to scan, right? Because if you don't have a clean surface, but instead you have pieces of metal in there, well, you're not going to be able to get your transducer and just like, you know, uh, slide it freely on that surface. Right? In order to detect both transverse and axial discontinuities, the weld has to be scanned in two directions from sides to side, right? So axial discontinuities, right, would be those discontinuities that are going along the axis of your weld. So maybe discontinuities in this direction, right? If you're looking for transverse discontinuities, right? Maybe you're looking for other type of discontinuities that might be oriented, right, in this direction, and that's why you're shooting at an angle in here, right, trying to get those to come back at you. And here, right, you scan back and forth, and you're going back and forth. Why? Because if you take a look a cross section of this, right, if you were to look at this plate, you would see that this, right, so this is your weld. So you want to scan, right, if it makes any sense. right? So that's why you want to move back and forth so you get the all this area covered. Right? Now you also want to oscillate your transducer, meaning moving it from left to right to catch any discontinuities that may not be perfectly aligned. So you move it, right? You oscillate a little bit, right? And you start moving it to the sides and doing this scan, that this scanning. Hmm. You will scan in those directions. As the probe is moved back and forth, the sound beam is required to overlap the previous scan by a given percent. The scan that shows on the left side of the image shows a scan pattern using a 50% overlap. So you want to always overlap on your scans, because if you don't, right? If let's say you scan uh, from here to here, well, this area you're not inspecting this area, and that's no good because you could have a problem there. So you want to make sure that you always scan. Right? If usually your spec will tell you how much they want you to overlap, right? If they don't tell you to overlap, right, a good practice is to overlap between 20, right, to 50%, right? They want to between 20 and 50%. They want to overlap. If they don't, that's a good practice though. Uh, if they tell you to do it at 10%, then you don't need to go all the way to 50%. Or if they tell you to do it 50, well, you don't do it at 20. You do it at whatever the procedure calls for, right? And the oscillation, right, the move left to right, right, you want to do it between 15 and 20%. Right? That's pretty much the standard. And they probably may not tell you this, but if they do, that's good. But if they don't, you usually want to do it 10 to 20%, 20 degrees to the left and right. Okay. As the transducer is moved back and forth, it should also be oscillated from side to side in order to detect discontinuities that may not be perfectly oriented at 90 degrees to the sound beam. Right? We said that. So in this case, we would only get indications that are perfectly at 90 degrees to the sound path. If we have an indication that is somewhat, let's say, that, if you're scanning with transducer 1, my sound beam may come here and may reflect out to the right, right, and we may not see that indication. But if we oscillate, right, this transducer a little bit to the left, maybe with transducer 2, right, having a new sound path, or not sound path, sound beam, right, maybe we can get that indication to come back at us at 90 degrees. Right? Most codes or standards require that the scan rate not exceed a minimum travel speed. A common practice is that the scan speed may not exceed 6 inches per second. Right? That's, you don't want to go too fast, right? They usually tell you about what the speed of scan should be, but if they don't, do not go above 6 inches per second. Right? The actual scan speed will be either detailed in governing specification or in one of the specification's reference documents. Before conducting the test, a set of reference points need to be scaled so that the locations of any discontinuities can be accurately identified. Okay? So another thing is that anytime you find a problem, discontinuity, or you find that if it's a weld, you may have lack of fusion. Anytime you find a problem, you want to always make a report on that, and you want to write what type, what scan you did, how you did it, from what phase you scanned, right? And you also want to make note of everything you find, right? So you have to map it. So the most common method used is the X and Y coordinate. right, where the x-axis represents the distance across the weld, and the y-axis represents the distance along the length. Right? So the x, right, would, if the middle here would be x0, right, as you start going in positive numbers, that means from the x to the top, right? This is just to identify problems in your weld, in your report, right? You want to make sure that they know where you found the problem. So this is your little way for you to do it, right? And obviously your y would be starting from 0 at the very left and increase as you move right. Okay. So if you have a problem here, right, you may say that 0, 8, and then you start counting, whether it be in inches or however you're doing it, and you tell them from where to where, right? Or if it's on this upper portion, you could say maybe it's x4, x5, depending on how you're measuring it, and you say, and it's located between y, whatever number that is, and this number. Okay? And you'll just measure this, and you'll give them those measurements, right? Whether it be in inches or centimeters. Right? And these are other methods in which, right, x would be 0 here, and y would start here again. Right? And then you would only have, let's say, positive numbers going in the down position. X would always be along this side, right? And y would be along the length. Okay. If it's a tube or a pipe, right, you want to go ahead and tell them x is the center, if it's right, and y would be the direction along. Starting, let's say, at the very top, you mark it, and then you say, okay, however many inches in the clockwise position or counterclockwise position. For pipe welds, it is a common place for the Y0 reference point on the top of the pipe for horizontal runs and in line with the elbow or fitting on the vertical runs. The X point is the center line of the weld. So, however, some codes do not have a specific conventions for this location, so they should be checked prior to setting the location marks. The distance of a discontinuity from Y0 is measured from the left of the weld to the nearest end of the discontinuity, right? This would be Y0, the very surface, and you start increasing as you start going or moving towards your other side of your weld. Therefore, a discontinuity that starts at 6 inches from the left, right, and ends from the left end of the weld and ends 8 inches from the left end must be listed as indication at 6 inches. Okay. When sizing the discontinuity for length, the technician should refer to the governing documents for direction. If a specific method for determining the endpoint is not given, it is common practice to use the 6 dB drop method for making that determination. Right? So we use the 6 dB drop method to mark where the discontinuity starts to where it ends. Right? And we're going to say how it works in a minute. If the 6 dB drop method is used, that fact should be recorded. So you want to let them know how that's, let me see if I have to picture that. So you want to let them know that that's how you recorded your indication, right? The 6 dB drop method refers to the fact that a decrease in 6 dBs will result in a decrease of strain amplitude of 50%, right? If you recall earlier with 20 log formula, we had said that anytime you increase 6 dBs, you're doubling your indication, right? Remember, we went from 40% all the way to 80%, and we said that we had to add 0.02 decibels. Well, if you increase 50%, right? If you decrease 50%, you will decrease your screen amplitude by half, or 50%. Or if you add, you're doubling your indication. the technician will manipulate the transducer to maximize the signal from the indication, right? So this is how we're going to do it, right? You will scan, and right when you get your indication, right, you will maximize your signal. You would put it at 80%. So you will, once you find a problem, you will put it right in the center of that problem, right? You'll move it back and forth. You'll move your transducer from side to side until you get the maximum amplitude, right? Meaning the most sound is being reflected back. Once you get the maximum amplitude, you will crank up your gain to 80%, right? And as you stay at 80%, now you're going to move your transducer, let's say, to the left, like in this, right? Now, as you start moving left, you're going to start, some of this sound is going to start going out, is going to start not touching that or reflecting back from that surface anymore, but instead going back all the way to the back wall, right? And as that starts happening, this amplitude will start decreasing, right? Because you have less sound reflecting off that interface. Maybe you'll have another one coming up here from your back wall, right? And you're gonna keep going left until the point that you're gonna see their indication is gonna come to 40%, or it's gonna be half of 80, right? So we know that our amplitude went from 80 to 40 just by moving it, right? So just by moving it left and right, we're gonna see that our indication is gonna. Why? Because the rest of the sound is gonna go all the way through to the interface, to the back wall, right over here. So as this starts dropping, the point at which, the position at which you have your transducer that this amplitude will drop down to 40%, you mark that, and that would be your start, right? Now you start scanning to the right again, and when you start scanning to the right, your amplitude will again go high as you get to the center of your indication, because you have all the sound being reflected. And as you keep going to the right, keep going, as you still keep going to the right, you're going to see their indication is going to start going down, and you're going to start seeing the little back wall, right? But again, to the point where it drops at 40%, you're going to mark that point, usually like halfway into your transducer, and then that's how you can map with a 6 dB drop, right? And 6 dB, not because you saw anything say that it dropped 6 decibels, but it's because we know that anytime we add or subtract 6 decibels, our amplitude will double or cut in half. So if we cut it in half, the amplitude, the reflection we're getting is less decibels less than the one from here, right? So that's the 6 dB drop method, right? And then you would go ahead and mark it, and that's how you would estimate how big your indication is going to be in your weld, or how long your axis. Since many discontinuities are irregular in shape, the technician should continue the sizing scan past the point at which the 50% amplitude drop is first seen. Right, so just because it dropped 50%, or it went 40%, it went half to the amplitude you had it at. If it was 80, we know we put it at 80. If it went at 40, you just don't stop there. You continue scanning, right? So if all you got is, if it dies there, then you mark it there. Otherwise, you just keep scanning. It is possible that the discontinuity will have a variant orientation that will drop off in amplitude at one point and then increase in amplitude again farther away from the center of the discontinuity. The 6 dB drop method, right? If the scan is stopped when the signal first dropped to 50%, the recorded length will not reflect the actual discontinuity length. If the acceptance-rejection criterion being used is based on the combination of length and decibel rating, miscalculation of the length could have serious results, right? So if we have a perfect straight line discontinuity like we have here, then we probably won't have much of a problem. right? Because when we get to this, right, if we go past this point, our indication is going to go lower and lower and lower, or the amplitude of our indication is just going to go lower and lower, right, until it dies. Right? But if you keep scanning here, and your indication goes, let's say, I start scanning here to the left, and it goes 40%. Well, if I keep scanning past this point and my indication keeps going down until it dies, then that's okay. I will mark this point. But if after 40% I keep scanning and the indication starts growing again, right? Maybe because it's not like this, and then it comes again flush, right? So maybe when I hit this, I'm going to reflect someplace else. My indication is going to go down, right? But then if I stop, if I keep scanning, I may see that my indication continues, and here, right, I'm going to have full reflection again, and it's going to increase, right? So what they say is, anytime you get to a drop of 6 dBs, continue scanning. Make sure that's the end of it, right? Make sure that when you keep scanning, your indication is not going to go back up, because maybe you had something like this again, you know? So, and that's because we had regular shapes, right? They're not, cracks are usually not straight lines 100%. The depth of the discontinuity can also be calculated using the trigonometric function based on the sound path and surface distance and the test angle. It can be read directly from graphic ultrasonic testing calculators, or with the newer machines it can be automatically calculated by pushing a button. Regardless of how the depth is calculated, the technician should bear in mind that the depth calculations is based on a nominal wedge angle of 45, 60, or 70. Those are the usual uh, angles at which we're gonna do shear wave, right, or length or angle beam inspection. Most codes and specifications allow the transducer to vary within a range of plus to minus 2 degrees. Right? As a result, a 3 decimal place depth of 0.002 centimeters may not be as accurate as the technician might think. Okay, and that's the end of chapter 6. And I got something else here. And what I'll do is next class, right, I will teach you how, if you have a plate, right, over here, and right, this is the thickness of your plate, and let's say you have a defect here. Let's say we're shooting this angle, this angle. I'm going to teach you how, knowing, right, the thickness and the angle at which you're shooting, how you can calculate the distance from your, if you have a problem here, right, how you can calculate the distance from your transducer, the surface distance, right, from your transducer to the defect, even though you only have access, your eye can only see right this upper surface, And I'm also going to tell you how deep that indication is from the top surface to the bottom surface by using some trig functions, right? Of sine, cosine, and also I think it's sine and tangent, right? How we're going to be able to pick this up using right? And when I'm going to we're going to go over what how we can use our machines and math, right, and these angles to calculate, right, how deep it is here. Or in the worst case, let's say we're also going to learn if your defect is here, how do we know how far is it from here to here, and how deep is it from here, from the top surface to the bottom surface, okay? We're going to go over that using some trig functions and some formulas I'm going to give you. But we'll leave that probably for tonight if we're going to meet again. And when you're a little more fresh, because this is going to take a little bit from you. Sounds good? Okay. So, what we got for today is go over chapter 6 again, okay? Do the quiz for chapter 6. And at night, we're going to go ahead and if we meet again tonight, maybe we can go over this problem, just this problem tonight, because I know it's going to be it's going to take a little bit. And then maybe tomorrow morning, early in the morning, we can go ahead and go over chapter 7. All right, guys? Any questions regarding this lesson, lesson 6?
No, I'm good. What about you, Augie?
No, I just noticed that, I tried following along with the student guide.
Okay.
I tried following along with student guide,
Uh-huh.
and it was pretty precise all the way until base metal testing or weld testing. Okay, from weld testing, you got a lot more deep or a lot deeper with your slides. So if you could fire off to me, either an email or something. If we're not going to get copies of the PowerPoint, if you could
Yeah,
fire
no,
off.
you will get copies of the PowerPoint.
Okay, I mean, I understand if the cost part of it. So if you
No, no,
want
no,
to
no.
email them,
Absolutely, no. I mean, the thing is that we were going to start classes today.
right, right,
I didn't know we were going to start like so early today. But
uh-huh.
because of that, yeah. But I gotta go get the books together. Mike, he wants me to send him the PowerPoints because he says he can print them at work.
Yeah.
So I mean, it depends on you, Augie. If you want, I can print you a book and give it to you, or if you want to go ahead and print it with Mike, that's also okay.
Well, I mean, why don't you send me why don't you send us why don't you send that to us and let me see how much it is as far as how much I can get away with printing. I can probably get it all printed, and that way you don't have to worry about it.
It's not a lot. It's not a lot.
Hey, then why don't you send us the PDF or whatever it is, or however
Yeah.
format you have it, and then we'll print it up. Okay?
I'll send
And
it
that
to
way
you
you don't have
today.
to worry about it. I'm sorry?
I'll send it to you today.
Okay, perfect.
Yeah.
Hey, and if you get a chance, send me those tests from the ultrasound level 1. Ultrasonic level 1. Remember?
Oh, the guides. the